A selection of prior binomial, two-point prior binomial and Gamma-Poisson based on lot size indexed by average lot quality, limiting quality level and acceptance quality level. Abstract. The theory of prior distributions is connected with theory of process control. Bayesian methods try to incorporate prior process knowledge to account for the variation in the sampling scheme. Though most of the acceptance sampling literature is based on classical methodology, there have been a few attempts to make the Bayesian paradigm to explain acceptance sampling techniques, most notably by Hald.A, 1981. The basic idea behind the Bayesian approach for calculating the sample size is to use prior information about the parameter p. The prior distribution is a key part of Bayesian sampling plan to represent the information about an uncertain parameter. This chapter gives the study on two-point prior binomial distribution and is used as a baseline distribution for designing the single sampling plan to determine the average acceptance and rejection cost with AQL and LQL. Necessary operating characteristic curves are sketched by highlighting with illustrations. Keywords: prior binomial, two-point prior binomial, Gamma-Poisson, AQL, LQL, ALQ, and OC. Introduction. The basic assumption underlying the theory of conventional sampling plans by attributes is that the lot or process fraction nonconforming is a constant, which intensively means that the production process is stable. However, in practice, the lots of products produced from a process may have quality variations due to random fluctuations. The variations in the lots can be separated into two, namely within lot and between lot variations. When the between lot variations more than the within lot variations, the proportion of nonconforming units in the lots will vary continuously. In such cases, the decision on the submitted lots should be made with the consideration of the between lot variations, and hence the conventional sampling schemes cannot be employed. A complete statistical model for basic sampling inspection contains three components. 1. The prior distribution is the expected distribution of submitted lots according to quality. 2. The cost of sampling inspection, acceptance, and rejection. 3. A class of sampling plan that usually defined by means of the restriction designed to give a production against acceptance lot of poor quality. The cost. Most of the research studies concentrated on sampling plans based on prior distribution and costs design by assuming that costs for guarantee and repair as well as marginal costs for sampling and rejecting an item. In this case, the main factors are inspecting and rejecting lots, passing defective items. Extra costs for repairing defective items are not considered. Since all the defective items have to be repaired either during the stage of sampling or when they are detected by the customer, by keeping the costs as constant, and therefore it is irrelevant for our purposes. If there is a difference in the repair costs, it will be integrated in the costs for passing defective items. Prior binomial distribution. The binomial distribution is frequently used to model the number of successes in a sample size n drawn with replacement from a population of size n. For larger n, the binomial distribution is a good approximation and widely used in a manufacturing process. The probability of observing x equals 0, 1, 2, n, non-conforming units among the n units of the sample is approximated by the prior binomial distribution. The probability density function is given by 0. P, x n p, equals nc x p x q n x equals 0, 1, n.0 p1, equals 1 p, 1. Conditions of application. Binomial distribution has the following four conditions. 1. The experiment consists of n identical trials. 2. Each trial results in one of the two outcomes, called success and failure. 3. The probability of success, denoted p, remains the same from trial to trial. 4. The n trials are independent. If the above four conditions are satisfied, then the random variable x is a number of successes in n trials is a binomial distribution with basic characteristics such as mean, standard deviation, and variance. X equals np var, x equals np, 1q, sd, x equals vnp, 1p. Develop and design the plan of single sampling plan for attributes based on prior binomial distribution for average acceptance cost. The linear cost model. The linear cost function is defined based on the study of Hald, 1981, for acceptance sampling by attributes for a single sampling plan, the product of quality pi, i.e., the product coming from product I equals 1, 2, 3, k. Ni, S1i and S2 ipi, plus, Ni and I, A1i and A2 ipi, lot is accepted with probability p, pi, Ni, S1i and S2 ipi, plus, Ni and I, R1i and R2 ipi, lot is rejected with probability 1p, pi, 2. The values of the constant can be found using the suggestions given by Hald.A, 1960. S1i, cost per item of sampling and testing. S2i, repair cost for a defective item found in sampling. A1i, cost per item associated with handling the, Ni and I, items not inspected in an accepted lot, frequently is 0. A2i, cost associated with a defective item which is accepted, may be quite large. R1i, cost per item of inspecting the remaining, Ni and I, items in a rejected lot. R2i, repair cost associated with a defective item in the remaining, Nn, items of a rejected lot. Logically expect that, S1 equals R1 and S2 equals R2, with equality frequently holding, since it should be no more expensive to sample or repair on a large scale on a small scale. The main aim of this research insists on finding optimum single sampling plans, NC, based on prior binomial distribution by minimizing the average acceptance cost K, and NCP, subject to the condition that A2, the cost associated with the defective items is minimum. Pa, P1, equals 1A, 3. Pa, P2, equals SS, or, Pa, P2, equals 1 SS, 4. Where P1 equals quality level corresponding to the producer's risk which is called acceptance. Quality level, AQL. P2 equals quality level corresponding to the consumer's risk called limiting. Quality level, LQL, K, and NCP, equals N plus, NN, A1 R1, plus, A2 R2, PP, P, plus, R1 plus R2 P, 5. KS, P, equals S1 plus S2 P K, P, equals A1 plus A2 P KR, P, equals R1 plus R2 P, 6. Operating procedure. The following procedure is used to determine the optimum values of single sampling plan, N, C, for the various values of the constant and is constructed with the following steps. Step -1, assume the acceptance number C equals 0. Step -2, define the lot size n and other constants S1, S2, A1, A2, R1, R2. Step 3, let A2 equals 31, minimum cost in initial stage is obtained with the minimum average acceptance cost K, and NC, subject to the condition A2 is small. Step 4, identify a single sampling plan, N, C, corresponding to the minimum average acceptance cost K, N, C. Step 5, repeat the step 1 by increasing the value of C, equals 1, 2, 8 and obtain SSP, N, C, based on minimum average acceptance cost for various values of N. 2-point prior binomial distribution. Two-point prior binomial distribution was given by Hald 6, 7, 8, 9 having the probability density function defined as f, p, equals w1, p equals p1 equals w2, p equals p1, 7. Where w2 equals 1 w1 and ws and ps are to be known. Properties of two-point prior binomial distribution. 1 if x is a random variable then pr, x equals 1, equals p equals 1 pr, x equals 1, equals 1. 2 the probability mass function of this distribution is f, k, p, equals p, if k equals 1 equals q equals 1 p, if equals 0. This can also be written as f, k, p, equals pk, 1p, 1k for k 0, 1, 8. 3 the mean of the distribution is e, x, equals p. 4 the variance of the distribution is v, x, equals pq. 5 the skewness of the distribution is 0.1 equals qpv/pq. 6 the kurtosis of the distribution is 0.2 equals 6p2-6p plus 1p, 1p. 7 the central moment of order k is given by k equals 1p, 1p, k plus p, 1p, k. Developing and designing the plan of single sampling plan for attributes based on two-point prior binomial distribution on acceptance cost k, and NCP. The main aim of this research insists on finding optimum single sampling plans, NC, based on two-point prior binomial distribution by minimizing the average acceptance cost k, and NCP, subject to the condition that A2, the cost associated with the defective items is minimum. Pa, P1, equals 1A, 9, Pa, P2, equals SS, or, Pa, P2, equals 1 SS, 10. Where P1 equals quality level corresponding to the producer's risk which is called acceptance. Quality level, AQL. P2 equals quality level corresponding to the consumer's risk which is called limiting. Quality level, LQL. K, and NCP, equals n plus nn.1 W1Q, P1, plus 0.2 W2Q, P2, 11.1 equals W1KR, P1, Ka, P1, KSKM slash 0.2 equals W2 Ka, P2, KR, P2, KSKM slash. Where KS equals W1KS, P1, plus W2KS, P2, KM equals W1 Ka, P1, plus W2KR, P2. In designing and modeling sampling plans under Bayesian theory, the two-point prior binomial distribution is considered. Tables from 4.2.1 to April 2, 20 are constructed to obtain the optimum single sampling plan with two-point prior distribution. The main objective is to minimize the cost function k, NINICI, with respect to AI, I equals 1, 2, 3, k. The costs such as replacement, cost of handling defective items and assembling and reassembling in the damaged parts and costs of renewed testing and inspection procedures are considered in the determination of the average cost regarding both acceptance and rejection cost for the AQL and LQL. Gamma-Poisson prior distribution. The Gamma-Poisson distribution with parameter p and the shape parameter m. P, d npm, equals, m plus d1, d. m1, npnp plus m, d, mnp plus m, md equals 0, 1. 12. Where p is process average, m equals scale parameter, d equals average number of defects. The OC function of SSP under the conditions of Gamma-Poisson distribution is then given by Pa, P, equals dot P, D, NPM, CD equals 0, 13. Conditions for the Gamma-Poisson prior distribution. Gamma-Poisson distribution is also called the negative binomial distribution and the conditions are 1. The number of trials, n is not fixed. 2. Each trial is independent. 3. Only 2 outcomes are possible. 4. Probability of success for each trial is constant. 5. A random variable is equal to the number of trials needed to make R successes. Develop and design the plan of single sampling plan for attributes based on Gamma-Poisson distribution for average acceptance cost. Bayesian inference concept is applied to design an optimum single sampling plans, NC, based on Gamma-Poisson distribution in quality control environments. To optimize the cost based on acceptance criteria known as average acceptance cost K, and NCP, satisfying the condition that A2, the cost related with the defective time is minimum. Hence we have employed a combination of costs and risk functions and tried to minimize the average acceptance cost K, and NCP, subject to the condition that A2, the cost associated with the defective items is minimum and satisfy the inequalities Pa, P1, equals 1A, 14, Pa, P2, equals SS, or, Pa, P2, equals 1 SS, 15. Where P1 equals quality level corresponding to the producer's risk which is called acceptance. Quality level, AQL. P2 equals quality level corresponding to the consumer's risk which is called limiting. Quality level, LQL. C is chosen as small as possible in P1 P2 and 1A, SS. This leads to a uniquely determined value of C in an interval for values of n, and all satisfying the conditions, we get K, and NCP, equals n, S1 plus S2P, plus, nn, A1 R1, plus, A2 R2, PP, P, plus, R1 plus R2P, 16. KS, P, equals S1 plus S2P Ka, P, equals A1 plus A2P KR, P, equals R1 plus R2P, 17. Where A1, cost per item associated with the handling the, nn, items not inspected in an acceptance lot, frequently it is 0. A2, cost associated with a defective item which is accepted, may be quite large. R1, cost per item of inspecting the remaining, nn, items in a rejected lot. R2, repair cost associated with a defective item in the, nn, items in a lot. S1, cost per item of sampling and testing. S2, repair cost for a defective item found in sampling. It presents a complete comparative study of the Bayesian optimum single sampling plan with the prior binomial, two-point prior binomial and Gamma-Poisson distributions based on acceptance cost and rejection cost. Corresponding operating curves are presented graphically for ease comparison. Comparison. In practice that the prior distribution is only vaguely known, it is important to get some information about how strongly the costs of the acceptance procedure are influenced by a change of prior distributions. For this purpose, the prior distributions with the same value are considered, namely. In the manufacturing environment the choosing the best distribution to apply depends not only on the effectiveness of lot size, sample size but also the average acceptance cost and rejection cost for both the consumer and producer. The following table gives a comparison of minimum average acceptance cost obtained by optimum single sampling plan using prior binomial, two-point prior, and Gamma-Poisson distributions. From the above table clearly indicates that irrespective of the lot sizes and the average acceptance cost are minimum at c equals 7, the optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in 2-point prior binomial distribution when compared to the prior binomial and Gamma-Poisson prior distribution. From the above table clearly indicates that, irrespective of the lot sizes and the average rejection cost are minimum at c equals 7, the optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in 2-point prior binomial distribution when compared to the prior binomial and Gamma-Poisson prior distribution. Based on the chosen optimum sampling plan at c equals 7, the average acceptance cost is compared for the lot size ranging from 1000 to 10,000 and its corresponding sample sizes with its p-value is given in the table 2. From this one can conclude that the 2-point prior binomial based on the average lot quality has the minimum average acceptance and average rejection cost for all the lot sizes with sample size less than that of the prior binomial and Gamma-Poisson distributions. Hence one can utilize the 2-point prior distribution as per the need of the shop floor situation. Comparison of prior binomial, 2-point prior and Gamma-Poisson prior distribution based on average lot quality p. In this OC curves of the measures such as average lot quality, acceptance quality level and limiting quality level are drawn for the fixed lot size n equals 1000 and 4000 based on the OC curves drawn when the lot size small. The OC curve seems to be identical for all the distributions with reduced sample size and cost. When the lot size increases, 2-point prior binomial and Gamma-Poisson are identical in nature and the sample size of 2-point prior binomial is minimum than that of Gamma-Poisson. The details are given in the table adjacent to the OC curves having the sample size and its associated cost. Several values are considered for the lot sizes. While lot size increases, the discrimination of the OC curve leads to ideal OC curve. The reader can visualize how producer's risk decreases without altering the consumer's risk. The decrease of the producer's risk by using such a scheme can be observed for each distribution considered in this study. From the above table clearly indicates that, irrespective of the lot sizes and the average acceptance cost are minimum at c equals 7, the optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in 2-point prior binomial distribution when compared to the prior binomial and Gamma-Poisson prior distribution. From the above table clearly indicates that, irrespective of the lot sizes and the average acceptance cost are minimum at c equals 7, the optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in 2-point prior binomial distribution when compared to the prior binomial and Gamma-Poisson prior distribution. Comparison of prior binomial, 2-point prior and Gamma-Poisson prior distribution based on AQL. Based on AQL, the OC curves are drawn for the optimum single sampling plan at c equals 7, lot sizes n equals 1000, 5000, 8000 shown in figures, 6.1.4, 6.1.5, 6.1.6. For the smaller lot sizes 1000, slider variation occurs for both producer and consumer risk, whereas for the larger lot sizes 8000, prior binomial distribution and Gamma-Poisson are identical in nature and gives identical OC curves. Fig 6.1.6, 2-point prior binomial gives a better result like smaller sample size and minimum acceptance and rejection costs with higher the probability of acceptance. The Gamma-Poisson is better because of lower values of p, when quality is maintained, at given higher probability of acceptance. Whereas for higher values of p, when quality is stated or low, it gives a much low probability of acceptance compared to 2-point prior or prior binomial distribution. Thus steeper is the OC curve, better is the plan. From the above table clearly indicates that, irrespective of the lot sizes and the average acceptance cost are minimum at c equals 7, in prior binomial distribution when compared to the 2-point prior binomial and Gamma-Poisson prior distribution. The optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in prior binomial distribution when compared to the 2-point prior binomial and Gamma-Poisson prior distribution. From the above table clearly indicates that, irrespective of the lot sizes and the average rejection cost are minimum at c equals 7, in prior binomial distribution when compared to the 2-point prior binomial and Gamma-Poisson prior distribution. The optimum sample size n and the value of a2, the cost of handling the defective items in assembling and disassembling is also very small in prior binomial distribution when compared to the 2-point prior binomial and Gamma-Poisson prior distribution. Comparison of prior binomial, 2-point prior and Gamma-Poisson prior distribution based on LQL. OC curve displays the discriminatory power of the single sampling plan, i.e., the OC curve of the sampling plan with 3 distributions at n, c is shown in the figure 6.2.1 based on the cost aspect according to ALQ the different p-values. The OC curves of prior binomial and Gamma-Poisson distribution are very similar, leading to ideal OC curve when lot size increases with increased sample sizes. Thus the precision for segregating good and bad lots increases with the size of the sample. The greater the slope of the OC curve, the greater the discriminatory power, thus Gamma-Poisson distribution is more advantageous than other distributions. Conclusion. For all the distributions, costs, and lot sizes taken into account, it turns that the costs saved by using the 2-point prior distribution are negligible. Accordingly, the OC curves of the optimum single sampling plans using prior binomial and Gamma-Poisson distributions are identical, whereas 2-point prior gives minimum value for average acceptance cost. Therefore, results obtained above suggest a more critical examination of whether there exist situations in which the prior distributions offer any practical advantage compared with the existing procedures and distributions, especially related with various costs faced in the inspection process.